So thanks a lot for giving me the opportunity to give this talk. I started in Warsaw relatively, well, already quite some time ago, but it seems like the virus is making things much slower. So yeah, this is my first formal interaction with your group. I'm very happy, and I hope there will be more in the future. And yeah, so actually I'll be talking about some work that I'm doing here with my group at the University of Warsaw. Let me just introduce them briefly. Maybe you know some of them already, at least for locals. So our group works on quantum information in quantum gravity. And we have one postdoc that just joined us from Paris, Dong Chenge, and also student Dimitrios Patramanis from Amsterdam, and a local student, Jan Borg. But the work I will be presenting today is based on collaborations I have done with a bunch of people in Kyoto, where I was a postdoc for quite some time before coming to Warsaw, and also with Javier Magan from Argentina. And the outline of my talk is as follows. I'll first give a motivation and background for our research, and I'll try to be pedagogical so people from various parts of quantum information and quantum computation will be hopefully able to follow the parts of holography and gravity that maybe are not your daily toys. Then I'll talk about some examples that are under kind of development at the moment, but I'll focus on a few of them, namely entanglement entropy and complexity in holography. These are the topics we are actively developing here in Warsaw as well. And then I'll talk about continuous tensor networks and complexity from path integrals. That's also our local product, or that's really a focus of these works I was doing in Kyoto. And then I'll conclude and post some open questions for discussions. So please stop me at any moment. I forgot to ask what was the code of the seminar, if you ask questions only at the end or during the talk.
So we ask during the talk, or
okay.
Chat, or okay, it's relatively flexible.
Okay, great. Then please stop me at any point if there's something you would like me to clarify.
Sure.
Okay, so actually, yeah, let me start with maybe a pedagogical or cartoonish introduction and the motivation. Why are we doing this? And why are we interested in quantum computation and quantum information from the perspective of holography and ADS-CFT? So actually, our main motivation comes from black holes. And for us, black holes are not necessarily the classical black holes in general relativity that we now know exist, and we can study them using gravitational waves. But we eventually would like to understand black holes as some objects where quantum mechanics and general relativity come together and are both important. So that's what I mean by kind of quantum black holes that we are studying, and we are asking various questions about them, for example, related to the information loss paradox, or the information that is being scrambled black holes when we throw something in, and so on and so forth. And this we do that in general with the motivation of understanding better the way to define the theory of quantum gravity, precisely where this quantum mechanics and general relativity would come into the game. So of course, this is a very old kind of holy grail of physics that many people in theoretical physics are trying to do. But a kind of new tool, relatively new tool that we are using is the so-called, to understand this quantum aspects of black hole, is the so-called ADS-CFT or holography that you might have heard before. And by some simple cartoon to understand this, I'll go into more details, but I like to think about ADS-CFT in the following way. So basically, ADS-CFT is some kind of well, it's some kind of setup where we can study and ask precise questions about quantum black holes by analyzing strongly coupled many-body systems at finite temperature. I'll really go into the details why we think that way and what is the precise map. But this is precise. This is maybe even a take-home message. If you don't remember anything from this talk except this slide, I will be very happy. So we are thinking about black hole objects as some particular strongly coupled many-body system, and we are applying, let's say in logic, this is called abductive reasoning. So we are applying a black hole test. For example, we look at particular many-body system, and we look at the entropy of that system, or the way the system scrambles information, or the way the system maybe destroys certain quantum information, or the way the system can perform complex operations. I'll also define that in a better way. Then, if the system is best in all these possible processes, in also another in kind of well-defined way, then this system behaves like a black hole, and then we think that this system is a good description of a quantum black hole in ADS, CFT, and holography. So this called this abductive reasoning was called by probably Polish logicians a duck test, where we think about a duck, that if something moves like a duck or quacks like a duck, then it probably is a duck. So this is the same test applied to black hole. And okay, so let me tell you a bit more about ADS, CFT, and holography in a more serious way. So ADS CFT is a setup where we actually study quantum gravity, or particular, well, in many examples, some string theory, or theory where quantum mechanics and gravity play a very important role together, and we study it in a box. And this box, we refer to the box as anti-de Sitter space. It's particular geometry in gravity. And on the boundary of that box, we have a many-body quantum system, usually referred to as a CFT, for conformal field theory. And the idea of ADS CFT is that actually this quantum gravity in the bulk of this box is exactly equivalent to this many-body system at the boundary. So it's conformal field theory in the boundary. And what I mean by this is that we can perform very complicated computations, or we can do a very complicated checks of this proposal in the boundary of this geometry. So inside this box, using quantum gravity or gravity, and then we can do similar computations in conformal field theory, but maybe not, of course, the conformal field theory. This was a theory at the boundary that doesn't have gravity in it, so we can do these computations in many-body systems, and we can actually check that they precisely match. So this is basically a rough cartoon of how we think about ADS CFT in the more precise terms. And in a sense that, so basically duality tells us that this dynamics of quantum gravity in the ADS box is exactly encoded in this quantum system in one lower dimensions. That's why we usually refer to it as holography. And generically, what this ADS CFT...
Can I ask you, Paweł? Can I ask you something?
Yes, please.
But this is a model, but I understand that this anti-de Sitter space is something very artificial. Yes, it's not physical space.
Yes. So it's some geometry. It's some solution of Einstein. When I talk about gravity, I mean some Einstein gravity here in this theory. But it's not our usual gravity, like the one that we live in, where we believe that the cosmological constant, for example, is very small but positive. So the Sitter space. It's a gravity with a negative cosmological constant. So in this sense, it is artificial. But many aspects, for example, of black holes that we can study are independent on this negative curvature that we find in the solutions that we find in this anti-de Sitter solutions here. So I will discuss this in a moment. Or maybe at the moment, like maybe a fair comment is that we can actually formulate this this prescription, this ADS-CFT for other spacetimes. So we can actually study it for flat space and for de Sitter. But the one that we understand the best at the moment, and then we can perform really precise checks, is the one with anti-de Sitter geometry in the gravity side. Does that answer your question?
Yes, thanks.
Okay, thanks. So generically, what ADS-CFT dictionary tells us is that a certain quantum mechanical system, the CFT, is exactly equivalent to some gravity theory in this ADS geometry in one dimension high. And this dictionary provides us with the following map. It tells us that certain quantum states in this quantum mechanical system, let's say some vacuum or thermal state, they're exactly dual to, or I mean dual equivalent to different space-time geometries. So for example, vacuum state is exactly equivalent to the empty space-time, so just empty ADS geometry. The thermal state is exactly equivalent to the black hole space-time in higher dimensions. So in particular, we can actually take this quantum mechanical system and study various observables here. And we can try to, and the question is, how do we recover these answers from the gravity side? But because we have the equivalence, we can also take some observables on the gravity side. We can do precise computations here, and then we can try to match them with the CFT. So this precise dictionary between ADS CFT it's actually something that we have been developing for almost 20 years now, and we understand it in specific examples very, very well and to great detail. So actually this idea it's actually very old. It comes from 't Hooft and Susskind, but it's been formulated in this precise manner by Maldacena, where he constructed several explicit examples of the ADS-CFT correspondence using string theory. And they will not be important in my talk, but I just wanted to stress that these cartoons that I've been drawing here, they actually have a very serious and concrete models and mathematics behind them. So in particular, this quantum gravity theory is a certain string theory on ADS backgrounds, and is exactly equivalent to some supersymmetric quantum field theory in 4 dimensions. So this is the original Maldacena's proposal. But we also have lower dimensional versions of this for gravity, for high spins, and so on. And these are very well tested and precise examples that we really understand. But actually, over the last, say 5 or even 10 years, we have been studying more and more toy models of this ADS-CFT correspondence, where still like many body systems or some simpler CFTs, maybe without supersymmetry and without all this fancy stuff that I'm writing here, like matrix models and so on and so forth, they show some aspects of gravity in a very similar way to ADS-CFT. And actually in these models, so in holographic CFTs in 2 dimensions or matrix models in lower dimensions, we have developed some very nice intuitions that take us very close or take us to the direction of quantum information and quantum computation. So in particular, connections with tensor networks as toy models for holography, or thinking about holography and as quantum error correcting codes, that has been very useful in the context of these toy models. And today I'll mostly talk about these toy models. Otherwise, I would have to introduce a lot of stuff that is not actually, that is a bit overkill. So I'll focus on these toy models. But actually, the big open question in ADS-CFT that we are still facing is the following. Even though we can test ADS-CFT in this extremely sophisticated mathematical model to really high precision, and we believe that at least in this setup is exactly true, we still don't understand the answer to the basic question, namely how quantum states in holographic models in the CFTs encode the information about gravity geometries. So but by that, I mean that once we are given this dictionary that we developed, we can check it in various setups and we find very good matching. But if you ask us like how exactly, like if you take a quantum mechanical system without gravity and you ask how exactly this state that you are giving me, or this quantum mechanical system, encodes the information about this geometry of ADS, we still don't know. We have some partial answers, but it's still something that we would like to understand, or we should understand better. And so maybe in other words, like even though the main point is that we study these quantum field theories, or for many years we are used to studying quantum field theories. That CFT is one of the examples of quantum field theories, like particle physicists, in a sense that we are computing correlation functions and observables and doing scattering processes. And this is very nice. These are useful observables, but actually this seems to be hiding the mechanism behind ADS CFT, or the question of how this CFT states hide information about gravity. But what we have observed over the last years in the studies of this toy models in particular, is that it's much more useful to think about ADS CFT and holography not as as particle physicists, but as quantum information theorists. So actually, when we think about, and I'll talk more about this in what follows, when we think about ADS CFT in the language of entanglement or complexity, actually we get much more information about the geometry of ADS than just by studying scattering in these processes. So our big motivation is actually now to study these black holes and in ADS CFT from the perspective of quantum information and understand how ADS CFT actually works.
Sorry, one question?
Yes.
So when you say we want to understand more about geometry of ADS, you mean geometry of a classical spacetime or some quantum effects in this spacetime?
Actually, both. Okay. So we want to understand the classical aspects of it, like how certain observables look in the semi-classical limit, but the most interesting aspects are exactly about these quantum aspects of black holes in these ADS geometries. That's an important point. Okay, so by studying this various models, explicit models, and also toy models for ADS CFT, but also studying quantum field theories in curved background. This is some program that is actually much older than ADS CFT. We have a certain set of constraints, or we have a certain set of, well, at least necessary condition for a many-body system to behave like a black hole. And then the constraints are as follows. So we think that black holes should be holographic in terms of entropy. I will elaborate on that in a moment. We also think that black holes should be the fastest scramblers of information. So when we throw something into a black hole, the black hole redistributes this information among its degrees of freedom, and it should be the fastest possible way one could do it in nature. This is an observation from this ADS CFT toy models. We also think that black holes should be capable of doing tasks of very high complexity, like for example, information paradox, things related to information paradox, if we can retrieve the information or not from the black hole. If we can, then it has to be some complex task to get it back. And in general, as a kind of a joke, you can think that black holes in these setups are the best in everything, in quantum information and quantum computation. But maybe the message from this introduction that I wanted to convey also is that the main kind of the most interesting part for me also for this program is that black holes motivate us to study these quantum field theories, the holographic quantum field theories, from the perspective of quantum information and quantum computation. So up to now, people mostly studied them from the perspective of really scattering processes and particle physics, but somehow now we are bringing all these interesting tools and in order to, from quantum information and computation, in order to understand black holes. But at the end of the day, we really need to develop these tools in the context of quantum field theories. So this is particularly my area of work, and that's what I'm doing for my everyday activities. Okay, so this was the end of the kind of pedagogical and motivational introduction. Are there some questions before I move to the aspects of entropy and more precise statements about information? Okay,
maybe I can just ask one thing, because I don't understand one element here, because we don't have quantum theory of gravity, yes? So, and on the other hand, you make some abstract model construction where you can, by some tricks, find some quantum effects in space-time. So what is like the basis of this, that this is really a correct physical description?
Okay, excellent. It's an excellent question. So the important thing is that we in ADS-CFT, at least we know that for sure in these explicit models, it provides us with one model of quantum gravity. It basically tells us that this quantum gravity in this strange space-time, it's an ADS space-time. So it still, remains to be seen, like how it, what does it have to do with our flat space and so on and so forth. But if you agree with me to study quantum gravity in this space-time, ADS-CFT tells us that exactly all the effects in this quantum gravity theory are hidden, or they are contained in this field theory at the boundary, in the CFT at the boundary. So in a sense, this is a definition, a non-perturbative definition of quantum gravity in ADS geometry that we have at the moment. We have it defined as a conformal field theory at the boundary. And what ADS-CFT tells us that everything that we want to know about quantum black holes, for example, in anti-de Sitter space, is exactly hidden in this conformal field theory. But it's hidden in a very complicated way. So we are trying to understand exactly how to extract this information about the quantum aspects of black hole from CFT.
Okay, but this is because I'm not an expert, but I know that there are some conflicting approaches to quantum gravity. So do you mean that in anti-de Sitter space, there is no ambiguity? Everybody agrees that this is the only quantum theory of gravity that is reasonable?
Oh, no. So okay. There are many other approaches, like canonical approaches to quantum gravity, loop quantum gravity, that ask different questions, or maybe they're interested in similar questions, but use different tools. So at the moment, the kind of advantage of this ADS-CFT is that it defines the quantum gravity theory in this geometry, and by studying this field theory allows us to do explicit computations.
Okay.
And this is by no means unique. So we hope that from this we will learn a lot, or we are already learning a lot about aspects of black holes. And with these explicit computations, we can just bring them on the table and discuss other approaches. If there is a computation from loop quantum gravity or from other approach that answers the same questions, then actually we can compare them and we can see if the answer from CFT is reasonable, from ADS-CFT is reasonable, or if we can actually have some serious comparison between various approaches. But at this moment, even though this precise derivations of ADS-CFT examples, they come from string theory, we are actually, the way I understand holography now is that it's much more general than string theory.
Maybe we'll get some two questions, because I see Michał unmuted.
Sorry. So
Michał Karpiński is unmuted. Maybe you wanted to ask a question or not?
Yes.
No.
No,
okay.
No, that was a mistake.
Oh, okay.
And Ricardo, you want to ask? No. Okay. Okay, so you can carry on.
Yeah.
I think there is a question in the chat.
Oh, there is, yes.
Okay.
Okay, so you can then you can either speak or you can just.
Shijing does anomaly CFT match with something? Okay, it's a technical question. Yeah, anomaly in the CFT match with the gravitational anomaly. It's got some gravitational action. It's a bit technical, but yeah, see, CFT is a UV description. Yes.
Okay.
Good. Yes, great. So, right. So indeed, let me just recap the question. Basically, for that question here, we are not assuming that this ADS-CFT have to be like the only quantum gravity theory and so on and so forth. It just gives us a very computable model in which we can answer questions about quantum aspects of black hole. but it still remains to be seen how it matches the general, like how it fits into the general program of, you know, defining a quantum gravity theory in the most general spacetimes. If it's a string theory or a loop quantum gravity, I don't think we have much to say at the moment. Okay, so basically what we all agree on, irrespectively of the approach, is that black holes should be holographic. And this is something that was shown to us by Bekenstein and Hawking a long time ago. And they actually derived that black holes should have an entropy that is proportional to the area of its horizon and not to its volume. So that means that somehow the degrees of freedom should be hidden in the boundary of that region that is hidden from us. And when we want to study black holes, or when we want to study systems like black holes, we are asking a question how generic this is. So can we study many-body systems where the entropy, in some sense, is holographic, in a sense, if it has an area law instead of a volume? And for many years, we've been wondering what is the nature of this area-like entropy, what are, for example, the states and so on. What is the what is the quantum statistical mechanics, but also quantum interpretation of these black holes? And people started thinking, like, that's where actually quantum information first kicked in. And people started thinking about this entanglement entanglement of a black hole as entanglement entropy or von Neumann entropy between the degrees of freedom outside and maybe inside that are hidden between us, that are hidden from us. So this was actually, so the question was, can we think about black holes in black hole entropy in terms of entanglement? And maybe for people that are not familiar, but I think probably everyone is familiar, is that the notion, and so how do we measure basically this entanglement entropy, or how do we compute it in many-body systems? Well, for that, let me just recap a very simple fact about quantum mechanics. So for example, we can consider a two-spin system, spin up and spin down, where we have a total Hilbert space of one spin and the other. And the basis vectors up and down. And we can consider two states, for example, the one where both spins are down, and the mixed state or entanglement state where we have a mixture between down and up. And when we compute the density matrices, okay, so then we define the density matrices respectively for the state chi and for the state psi. And then we can compute a reduced density matrix of a first spin. So this is usually defined by tracing over the Hilbert space of the second spin, and the same we can do it for the state psi. So we can check that the reduced density matrix of the first spin is just a diagonal with one on the first entry, and the one of the second spin of the first spin, the second state psi, is basically diagonal with 1/2 on the diagonal. So one way to measure entanglement, or to characterize the entanglement in particular in the state psi and psi, is the so-called von Neumann entropy or entanglement entropy, and this is the notion I'll be using. So for example, so we define it as a trace of this reduced density matrix of the first spin times the logarithm of the reduced density matrix of the first spin. And because both of the states are pure, the entanglement of the first spin is actually equal to its complement, so entanglement of the second spin. And we can check that this von Neumann entropy in the state chi was simply 0, and in the state psi is log 2. So it actually measures if it's 0 or non-zero, it measures for us if the state is entangled or not in this bipartition. So this is the notion. I'll try to that people immediately try to understand applying to black holes. Can we understand this entropy of a black hole in terms of von Neumann entropy? And this was actually an old computation by Średnicki in '93, where he actually wanted to take a many-body system. So say some local Hamiltonian in some number of dimensions, say free scalar, and compute entanglement entropy between some degrees of freedom in some region A and some degrees of freedom outside that region. So there's no black hole, it's a black hole motivated computation in many-body system. And then in this free theory, he could actually compute the von Neumann entropy, and he noticed that that the entanglement entropy of this region A it's again in the vacuum of some Hamiltonian 4D, for example, is proportional to the area, not to the volume of this region A. So in some sense, this tells us that black holes, maybe if we think about entanglement, if we think about black hole entropy as entanglement between some region outside and inside, maybe they are not so generic. And even some many-body systems in their vacuum, they show an areal. This was actually a very interesting computation that started a lot of important developments, but it's still it has several drawbacks that are still pushing our field even up to today. So, for example, we see that there's indeed an areal for the entropy, but the answer is actually divergence. So, in order to do a computation in quantum field theory, we need to regulate it, and actually the answer depends on the cutoff. So, actually, to remove this cutoff to get a finite theory, we actually believe that we should have, or to do this computation explicitly for the black hole, we will need actually the theory of quantum gravity. And so far we don't have to do this computation explicitly. But actually, so this was actually our first lesson where we learned that quantum information may be very useful in using tools from our quantum information may be very useful to understand black holes. And then actually many years, almost more than a decade later, in the context of ADS-CFT, actually Ryu and Takeyanagi, they proposed an holographic formula for entanglement entropy in conformal field theories. And their formula again is kind of an extension of a Bekenstein-Hawking entropy, but for subregions. So they propose that if we take a CFT, very similarly to the computation of Średnicki, let's say now we take a conformal field theory and then we take some subregion A and compute entanglement entropy between A and B in any state we want, then actually the answer you're going to get for entanglement entropy, for von Neumann entropy in the state, can be reproduced from the gravity by the area of a minimal surface that stretches into this ADS geometry at some constant time slice, that is of the surface that is attached to this region A at the boundary. And first, they noticed actually that there were many computations done in two-dimensional conformal field theories that provided explicit results for entanglement entropies in various states due to Cardi and Calabrese, and they managed to show that the minimal surfaces in three-dimensional ADS geometries, they perfectly reproduce all these answers. But later, Maldacena and Lewkowicz, they managed to derive this formula, the Ryu-Takeyanagi formula, starting from gravity in ADS. So this led to many interesting developments in ADS-CFT, in particular tensor network or quantum information related developments. And this also led to our collaboration from Simon's Foundation, Eat from Qubit, that actually brings together this quantum info and holography people. So that's like the first part of the story, namely the entanglement. That's one of the first tools that we are using in ADS-CFT. But then coming back to our question about understanding ADS-CFT, or namely how states in quantum mechanical systems in these conformal field theories hide or contain information about gravity, we are coming to the story of ADS-CFT and tensor networks. So actually, also several years ago, Guy Vidal and Brian Swingle, they actually noticed that when you look at the particular tensor networks that are efficient representations of many-body wave functions for conformal field theories, so something called Meran, the tensor network. Actually, these tensor networks for CFTs, they look very much like time slices of ADS spacetimes. So these ADS spacetimes are examples of hyperbolic geometry. So here you can see the disk, the visualization of geometry by Escher. hyperdipolic geometry by Escher, and they noticed that actually maybe we could think about geometry from conformal field theories in terms of basically geometry of tensor networks. So in a way that once we represent the state of many-body system, and then we optimize it, then in some kind of classical like limit, we could think about this classical geometry as a continuous version of the tensor network. And this was a very useful hint. And in particular, one of the strong points of this observation was that when we compute entanglement entropy of some subregion of the degrees of freedom in this conformal field theory, so let's say we take this to be region A and to be complement, the entanglement entropy of this region is estimated by a cut through the network, a minimal cut through the network, and this cut is exactly equivalent to the Ryutaka-Yanagi proposal for entanglement entropy on the gravity. So actually from this idea, people thought that, okay, maybe if we know all the entanglement structure in the quantum state of a CFT, then we should be able to tell what is the dual geometry of that state, in a sense that if we know all the entanglement entropies in a particular state, we would know all the geodesics or all the minimal surfaces in this geometry, and from that we could recover the geometry of ADS. And this led to an idea or kind of paradigm that we should be able to understand geometry of holography from entanglement or from quantum information. Another observation was also due to Van Ramsdonk some years later, that actually entanglement in many-body quantum system leads to connectedness of spacetime. The example of a state, this is kind of a slogan, but the example of state that we studied and that we like to study in ADS-CFT is the so-called thermofield double. It's a purification of a thermal state. So say I take two states, two thermal state of this particular systems, or two copies of a particular system at some inverse temperature beta, and I put them into this entangled state, maximally entangled state. Then we actually can check from ADS-CFT that this is now dual not to just a single black hole or two black holes, because as I was telling you before, the just single thermal state in the CFT is actually equivalent by ADS-CFT to a black hole geometry. But this state that is very much entangled is actually dual to so-called the wormhole geometry in ADS-CFT. So I'm not sure people are familiar with this Penrose diagram representation of geometry, but basically what this picture says is that this state is dual to two black holes. So we have this black hole here on the right and black hole here on the right, on the left. They have some singularity in the future and the past, but actually these black holes are now connected by the so-called Einstein-Rosen bridge. So this led to a paradigm actually that this strengthened this intuition that indeed entanglement may be the key to understanding the geometry, and in particular, if we take some states that are very entangled, the dual geometries on the holographic side, they have wormholes in them. Okay, are there any questions about this part? Okay, good. Yes, and then so the next, basically the next thing I want to review is the idea of complexity, or how the idea of complexity appeared in ADS-CFT, and why are we thinking about complexity of state in many-body systems. So as I told you, this way of thinking about the ADS-CFT in terms of tensor networks as toy models for ADS-CFT is very useful, and basically tells us that by studying the tensor networks, like the Mera-like tensor networks, and exploring the entanglement structure in quantum states, we could actually rid of the geometry on the gravity side. But so for many years, we thought that this program is it's kind of complete. We just need to understand the entanglement structure in all the states of CFTs, and then we'll exactly know what the gravity geometries are. But actually, Maldacena and Hartmann provided us with kind of counter example to this program. So here in the previous slide, I showed you this thermophile double state, that is the entangled or purification of a thermal state, this entangled state of two thermal systems. They show that if we actually perform a time evolution with a particular Hamiltonian, so here this, you can think about this as two systems with some Hamiltonian, two copies of the same system with some left Hamiltonian and right Hamiltonian, and they showed that if we perform the time evolution of this thermophile double state, actually the tensor network picture gives us a little bit surprising answers. So for example, at time t equals to 0, the tensor network representation of this thermophile double state is actually as follows. We have these two asymptotic regions where we have one CFT and the other CFT, and they are just connected by some network in the bottom. But once we perform time evolution, this tensor network, in order to reproduce some answers for entanglement, entropy, and correlations, we see that these tensor networks have to grow with time. So in a sense that if we want to represent this state for later times, we need to add and add more tensors in the layer in between those two boundaries. But on the other hand, if we compute entanglement entropies between some region A on one boundary and some region B on the other boundary, we actually quickly see that this entanglement entropy first grows linearly, which is a good sign, but then very quickly it saturates, almost after the time of order the size of the interval A and size of the interval B. So in some sense, we can see that this geometry that we are, so this tensor network that they are describing has some feature in it that grows with time, but entanglement entropy seems to be blind to it because it saturates the constant value after very quick times. In terms of the gravity picture, maybe the better picture would be the wormhole that I showed you at the very first slide. But in terms of the gravity, we can actually see that more explicitly geometrically, that actually as we evolve this system with time, what grows is actually the size of the wormhole that connects two black holes spacetimes on asymptotic regions. So actually, Susskind noticed that, and he came up with a slogan that actually entanglement entropy is not enough to understand holographic geometries. And we need something more, some additional maybe quantum information tools to fully capture geometry of quantum states or to gravity in terms of quantum states. And basically he asked the question, what is the field, the quantum mechanical or the CFT dual of this growth of the Einstein-Rosen bridge? And he proposed that actually this should be some notion of complexity of this quantum state that we are talking about, that should be related with the number of tensors that is needed in this optimal tensor network. And with his collaborator, he actually proposed two notions of this one. So I showed you that, for example, Ryutake Yanagi gave the holographic prescription for computing entanglement entropy from gravity and then matching it to CFT. Susskind and his collaborators, they gave two prescriptions of what should be the notion of complexity of this quantum state, or what should be a good measure of complexity of quantum state from gravity. So one of this notion is so-called volume of the gravity. Basically, again, I'm sorry for this picture if you're not familiar, but this is, again, some two black hole spacetime connected by a wormhole, Einstein-Rosen bridge. And this, the red line here is actually the extremal volume that of a slice that goes through the Einstein-Rosen bridge. That was one good quantity from gravity that could be a nice measure of complexity. The other proposal was the gravitational action evaluated on a certain patch of the geometry that also has this property that grows linearly with time for times much later than the entropy saturates. So these gravitational observables would be good quantities that would actually tell us something about physics here after saturation of entanglement.
I will have some 5 minutes more. Okay,
great. I think, yeah, maybe I'll be very quick here. So, so what do we, but of like, as far as we know a lot about quantum entanglement in quantum many-body systems, actually the complexity in quantum mechanical system and quantum field theories is much less known. I mean, the notion of complexity in quantum field theory is much less developed, let's say. But what we know is actually that in any quantum mechanical system, so this is some famous theorem due to Margolus and Levitin, in any quantum mechanical system under unitary evolution, the system can can pass at most through m over h bar states, where m is the average energy in particular of the particular state. So in terms of computational complexity, actually the rate of production of complexity is bounded from above by this average energy and h bar. And actually, Susskind and his collaborators, they managed to show that if they, well, up to some normalization, if they actually look at this complexity cause-action proposal, it seems to be saturated for many, many black holes in ADS. So they seems to be the objects that produce complexity the most in the maximal possible way. But then how do we actually define complexity in quantum mechanical systems? So actually one idea that came very early is the so-called idea of circuit complexity, where we basically look at two states, some reference state and some target state. For example, you can think about this entangled and and product state that I showed you at the beginning. And we choose some number of gates, some set of gates in our system. So for example, C0 and Hadamard that can take us in the most efficient way from one state to the other, and then we count the complexity, or we define the complexity as the number of gates in this optimal quantum circuit. So now what we are trying to understand now is how to generalize these ideas into many-body systems and to strongly interacting CFTs. And that's one of the big goals of our program that we're also pursuing here in Warsaw. Yeah, because I don't have time, I'll skip this part, but I just maybe wanted to tell you that there's a natural way to generalize this concept into many spins due to Nielsen that has to do with some geometry of unitaries, or basically thinking about complexity in a geometric way as some geodesics on the manifold of unitaries that plays to be very useful. And that's what I've been involved in these works with Javier Magan in 2019. But yeah, let me just quickly go to the very last part or maybe like the kind of final message is that actually all these quantum information tools are extremely nice, useful, and natural to think about holographic geometries from the perspective of CFT. But we are somehow bounded to the thinking about quantum field theories as in terms of particle physics observables. So one good way to proceed, or good way to define things in terms of quantum information is actually to use the path integral methods in quantum field theories. And if we start from path integral, the path integral, Feynman path integral that you learn about in quantum mechanics courses. So it's somehow goal of our project is that is to use this definition of quantum states in many-body system in terms of path integral and try to extract from them entanglement and complexity and other quantum information measures that will allow us to determine holographic geometries in the kind of optimal possible way. So I don't have time to discuss this also, but there's a natural way to define complexity of path integrals that we have done in Kyoto, and this seems to be a very fruitful and promising way to go into strongly interacting many-body systems. And what we are working on now is trying to understand how these notions, these path integral notions of entanglement and complexity can be reproduced from gravity. So, okay, so that's all I wanted to say in this kind of general and pedagogical review, hopefully. I wanted to say that black holes motivate us to develop and understand quantum field theories from the perspective of quantum information and computation. It seems like what we are noticing is that classical general relativity seems to be corresponding to extreme quantum regime, where basically classical black holes or classical and semi-classical aspects of black holes seem to be telling us about something about extreme quantum systems in terms of scrambling or sending quantum information from one region to another. What I didn't have much time to talk about, but I wanted to stress is that path integral in quantum information is something very useful and seems to be a way to go beyond simple 2-qubit systems. And somehow the the program we are realizing now is how to define complexity in many-body quantum systems, and from that we would like to understand something beyond entanglement and something that hopefully has all the information about dynamics of gravity. Yeah, and the open questions are the ones I posted at the beginning. So what is the basic mechanism behind ADS-CFT, why it works so well, how to extract the geometry from quantum states, which black holes are actually dual to quantum field theories and vice versa, and how much quantum information tools do we need? Is complexity enough? Do we need maybe some fidelity measures, more information from tensor networks? Should that provide us with enough information to actually understand ADS-CFT? That remains to be seen. But any ideas and input from quantum info will be welcome. So I hope this will be a start to our collaborations and discussions. Thank you very much.
Thanks a lot. This was a very inspiring talk. So we have some time for questions. Janek has a question.
Yes, hello. Thank you for a very nice talk. I wanted to ask about this connection between speed limits because you went very fast.
Yes, yes.
So I understand, please correct me so I would like to understand how did Saskin et al., you showed many pictures, proven that some kind of these models that they have saturate this kind of Morgulus-Levitin bound. So I want to just conceptually, I understand that they take some model of complexity in the anti-de Sitter space of the black hole, then they translate it onto CFT, and then from the CFT and the many-body system, they compute this speed, or is it the speed already in the anti-de Sitter space?
Yeah. So okay, good. So the way we do things in holography is in some sense indeed as you said. So we can do computation in conformal field theory, but we can also do computation on the gravity side. And when we have this dictionary or proposal how things should work, then we can actually check that the answer is match. Okay, so for example, for entanglement, we compute entanglement for Neumann entropy in conformal field theory. This gives us some number that depends on the size of the interval, the central charge, and so on. Then we can take this minimal surface in ADS geometry, and then this gives us another number that depends on the size and so on. But there are some parameters that we know how to match in ADS-CFT, but once we relate these parameters, we see that these two answers match. So what Saskin, we can actually, in complexity, we do something very similar. So what Saskin did is that they use this definition of complexity in terms of some gravitational action computed on this geometry background, on this black hole background. And then they said that, okay, if we actually, if this is our definition of complexity from the bulk side, from the gravity side, this is a good measure, then, first of all, they computed it for various black hole examples. And what they checked is that if they take the derivative of this gravitational action with respect to time, it precisely saturates this bound.
So this average energy is some kind of evaluated for the black hole, not...
Yes, it is exactly. It is evaluated for the black hole.
Okay.
Yes. But in some sense, yeah, we cannot, there's no computation of this quantity or this bound from the CFT side yet, from the field theory side yet. So that's what we are somehow working on. That's the goal of the program, try to find maybe a good measure of complexity from the field theory side that can be applied to this thermofield double state that evolves with time. And hopefully we can also check this bound from, if we can check if CFT first of all matches this answer and if it satisfies this Margolus-Levitin bound.
Okay, you have another question from Marcin?
Yes. Thank you for a very good talk. So my question is that if I understand this correctly, this ADS-CFT correspondence is about connecting the geometrical features of space-time and some quantum objects. So, for example, you showed that area corresponds to the entropy, and we here know very much about quantum, let's say, object called quantum feature information, and various kinds of it. So we know how it behaves when you have entanglement in your system, how it behaves when you have no entanglement there. And well, and it also connects to those quantum speed limits. You can derive them through this quantum Fisher information. So do you know if there is any geometrical interpretation in terms of this ADS-CFT of quantum Fisher information?
That's a great question, actually. So in some sense, your question is exactly what our business is about. So we're interested in somehow quantum informational tools that are universal enough that we know a lot about, and that we can use in ADS-CFT to learn something about the geometry. So in some sense, if there are some useful things, like for example relative entropy or distance measure between quantum states, then we know how to compute them in conformal field theories, and then we can try to see what do they correspond to in terms of gravity. And in terms of Fisher information, I think there's like a Bures distance that the closest connection to that we know is that also by Takayanagi and collaborators, they managed to show that if you compute this Bures distance between quantum states in conformal field theories perturbed by some operators, then it actually corresponds to some volumes in the bulk in ADS geometry, some so-called maximal volumes. And I think this has been tested and checked to in a lot of examples, but I don't think I'm not sure how many of these quantum informational properties of the distance or Fisher information metric were really checked on the holographic side. So maybe it's a good idea to explore further.
Okay.
Thank you.
So any more questions?
Maybe a follow-up from what Marcin asked, very short. So is there a way to translate a metric in the bulk onto the metric in the CFT? I mean, we don't know how to calculate metrics in CFT, but if there is such a notion, because this is what I think Marcin is asking.
Yeah, so indeed the metrics between, so basically distance measures between quantum states, they are very important and useful for us in some sense. When I mean complexity here in these talks, I'm talking about some need for a good distance measure in field theory that would have a very good geometric interpretation. And so in the field theory, I agree the metrics are important. On the gravity side, the metric itself is not it is important, but it's not like the metric on the gravitational metric is directly related to the metric between, of the distance metric between quantum states. We use it to compute certain distances in the gravitational geometry, but it's not like simple one-to-one correspondence. So in some sense, in some sense, your question is very good, but it's somehow, that's something that we are really trying to understand from this program, like what gravitational objects, like what gravitational quantities have corresponding what the quantity in terms of quantum information tools. So far we have things like kind of defined in a, say, covariant way. So for example, we can look at areas or volumes and things like that in the geometry of ADS. Mm-hmm. But the correspondence between particular metrics here and there, it's still not clear, except of course that it's clear in a sense that we know that one metric represents particular state. But we can change, for example, on the gravity side, we have we have a freedom of redefining our coordinates, so we can locally change coordinate system, and then this diffeomorphism invariance and the bulk, it's something that is that doesn't favor one particular.
In a sense, metric in the bulk is not that interesting. You're saying. Okay.
Okay, maybe we can have some last question.
Yes, sorry. Thank you.
Marcin, yes, you wanted to ask something, or?
No, I just wanted to comment. So if someone has a question, then
maybe
please ask
someone has some short, concrete question, then one may ask. And If not, then Martin may comment. Okay, so I think
Yes,
that
I can make a comment. Yes.
yes, I think you can comment.
Yes. So because maybe what I agree. I agree that well, maybe the metrics on the gravity side, well, as you said, maybe they are not so important. But well, the metrics on the quantum side, they basically quantify the, well, let's say, distinguishability or the disturbances in various quantities, like, I don't know, like free energy or, well, whatever you can come up with. So I simply think that it will be very interesting to somehow translate those disturbances to this gravity picture, because we know a lot about the relations of the quantum metrics. I mean, the metrics on the space of quantum states, how they relate to each other, what are the inequalities between them, how they behave in the presence of entanglement. So I don't know. I think just that this is a nice place to work.
Yeah, I agree. As long as, I mean, yeah, this is something I hope we can discuss more. As long as we have some quantum information tools that can be defined naturally and for infinite dimensional Hilbert spaces that we encounter in conformal field theories, but quantum field theories, then they are very useful tools for ADS CFT. So
I think we have to stop here. So thanks a lot for this great talk.